Business Statistics 2. Study Session 1. Random Sampling and the Sampling Distributions. Introduction. This study session will introduce you to random sampling, sampling distributions of means, proportions, estimation, and hypothesis testing, correlation, and regression analysis. Sample and elements of statistical sampling. In a word, samples are useful in providing information about the characteristics of populations when time and money, or both, are important factors. Oftentimes in a real-world situation, a complete enumeration of all sample units in a population is too costly or too time-consuming. Certainly, in cases of infinite or extremely large populations, a sample is required because a complete enumeration is impractical, if not impossible. In summary, some of the major reasons why sampling is necessary are: 1. The destructive nature of certain tests. 2. The physical impossibility of checking all items in the population. 3. The cost of studying all the items in a population is often prohibitive. 4. The adequacy of sample results. 5. To contact the whole population would often be time-consuming. Precision and accuracy. For a simple random sample, we usually measure the precision of the sample by the standard error. For a particular universe, the lower standard error means more precision, less variance in the sampling distribution. But using the standard error as a measure of precision relates only to the chance, or sampling error, involved. All three of the factors may contribute to a difference between the estimator and its parameter. 1. Sampling, or an internal error, is measured by the standard error. It is caused by the fact that a sample is taken. 2. External error is an error related to the practical considerations in taking a sample. These errors are usually caused by the people conducting the sample and processing the data. 3. Bias, viewed from practical consideration, can be the most insidious of the three factors causing deviation between the estimator and the parameter because it may be difficult to detect. Random versus non-random sampling. In general, there are two types of samples, a probability sample, and a non-probability sample. A random or probability sample is a sample in which the probability of any item in the population being selected is known. If probability sampling is done, each item in the population has a chance of being chosen. If non-probability methods are used, not all items or people have a chance of being included in the sample. The main advantages of random samples are: 1. They depend on random outcomes, not the judgment of the sampler, and are more likely to be representative. 2. The result is a probability distribution for which the magnitude of interval error can be estimated. Types of random samples. There is no one best method of selecting a probability sample from a population of interest. 1. A method used to select a sample of invoices in a file drawer might not be the most appropriate. 2. A method to use when choosing a national sample of voters. 3. Methods have a similar goal, namely, to allow the chance to determine the items or persons to be included in the sample. Simple random sample. A simple random sample requires that the sample be taken in such a way that each sample in the universe has an equal probability of being selected. The technique for selecting a simple random sample is, in fact, reasonably simple. Systematic sampling. Systematic sampling may really be considered a method of selection when compared to simple random sampling. Thus, most random sample designs use one or both of these methods of selection. Systematic sampling is drawn by selecting every item in a universe. Referring back to our example with the credit customers, if we selected every 100th customer in our universe for the sample, we would be taking a systematic sample. Other examples are to select every 4th house in a series of blocks, every 50th pay voucher, or every 30th car passing an intersection. Stratified sample. Another modification of the simple random design is the stratified sample. This sample design gets its name from the division of sample elements in the population strata or layers. When a population is heterogeneous overall but within it are homogeneous subpopulations or strata, it is usually desirable to divide the population into these strata. Items for the sample are selected from each of the strata rather than the universe as a whole, depending on the population to be sampled. Cluster sample. Another form of a modified random sample design is called the cluster sample. Like the stratified sample, the cluster sample design requires that the sample units be grouped. Unlike the stratified sample, the sample units are grouped by clusters in the universe, not homogeneous strata in the population. The sample unit consists of more than one sample element. An entire cluster or group of elements is randomly selected, and all or part of the elements in the cluster are included in the sample. Thus, the sample unit is the cluster of elements. When dividing a universe into clusters, care should be taken to avoid any overlap of the clusters. Multi-stage sampling. The sample designs that have been mentioned are considered the basic ones among the sample selection procedures. There are others, but these four. 1. Simple random sample. 2. Systematic sample. 3. Stratified sample. 4. Cluster sample. Sampling size and cost analysis. In statistical sampling, the cost of the sample and sample size are so interrelated that it is difficult to consider one without the other. 4. Other things being equal, you would expect the cost to vary with the sample size. Therefore, in developing a sample design for a given situation, cost and sample size are important considerations. The two important factors affecting the size of a sample, other than costs, are 1. Level of accuracy or precision desired. 2. Variability of the items in the population. Sampling cost. There are both fixed and variable costs associated with taking a sample. It is usually less expensive to take a sample than to do a complete enumeration, examine 100% of the universe. Yet the cost of taking a sample of n items may vary considerably from one sample design to another. Sample efficiency. In designing a sample, we must be concerned with sample efficiency. Sample efficiency deals with achieving the greatest accuracy or precision of sample results for a given cost of the sample. Here, again, we are talking about cost, accuracy, variability, and sample size. Thus, in designing an efficient sample we should consider the following. 1. Given a desired level of efficiency, a sample design should be selected which provides the minimum cost for a certain size sample. 2. Given a level of expenditure, the sample design selected should provide maximum precision. In either case, we should try to optimize one or the other. The sampling distribution of sample means and proportions. A simple random sample for an infinite population is a sample of size n selected so that each element of the universe has an equal chance of being chosen as a sample unit. This results in each sample of n items having an equal chance of being selected. Thus, it is apparent that this is the same definition of a simple random sample as that given for a finite population. Under the infinite population, however, the assumption of independence is met. Obviously, this is the case with replacement, but not the case without replacement. Sampling from a finite population. The preceding discussion was for sampling from an infinite population. However, sampling from finite populations is more likely to occur in business applications. Thus, we must investigate the effect of the finite population on the estimate of the parameters for the sampling distribution. To avoid overcomplicating the situation, it will suffice to say that there is an effect on the estimation procedure due to the finite population, but that this effect can be corrected. Summary for Study Session 1. In this study session, please note the following. 1. Statistical methods are those procedures used in the collection, classification, evaluation, and interpretation of data. The applications of statistics can be divided into two major areas, descriptive statistics and inferential statistics. 2. The emphasis in business statistics is on inferential statistics. Inferential statistics, also called statistical inference or inductive statistics, utilizes sample data to make estimates, decisions, predictions, or other generalizations about a larger set of data. 3. The random sampling and sampling distributions of means and proportions, estimation, hypothesis testing, and correlation and regression analysis were also discussed. Study Session 2. Sampling Error. Introduction. Sampling error is the error that arises in a data collection process as a result of taking a sample from a population rather than using the whole population. Sampling error is one of two reasons for the difference between an estimate of a population parameter and the true, but unknown, value of the population parameter. The other reason is non-sampling error. Using the sampling distribution of sample means. Logically, it is unlikely that a sample mean would be identical to the population mean. Likewise, the sample standard deviation or other measure computed from a sample would probably not be exactly equal to the corresponding population value. We can therefore expect some difference between a sample statistic, such as the sample mean or sample standard deviation, and the corresponding population parameter. The sampling distribution of sample proportions. So far, we have discussed sampling distributions of the arithmetic mean. There will be times, however, when the statistic of interest will not be the arithmetic mean. That is, the statistic might be a percentage sometimes, referred to as a proportion. Since this is the case, We must investigate how sample proportions are distributed, where P is defined as the ratio of the number of successes to the total number of events, in a binomial situation. As before, if we sample from a finite population, we should use the finite correction factor. Now that you are familiar with the sampling distributions of sample proportions, you need to learn to make use of it. Since the central limit theorem applies to sample proportions, we have an equation for converting the sampling distribution to a standard normal distribution. Summary for Study Session 2. In this study session, please note the following. 1. That a sample means would be identical to the population mean. Likewise, the sample standard deviation or other measure computed from a sample would probably not be exactly equal to the corresponding population value. 2. We can therefore expect some difference between a sample statistic, such as the sample mean or sample standard deviation, and the corresponding population parameter. 3. The difference between a sample statistic and a population parameter is called the sampling error. This error is simply due to chance. Suppose a population of 5 production employees had an efficiency rating of 97, 103, 96, 99, and 105. Study Session 3. Confidence Interval and Statistical Hypothesis Testing for One Population. Introduction. This study session will be focusing on estimation and investigate statistical hypothesis testing with the objective of making inferences about a population mean or proportion. We are first going to examine confidence interval and statistical hypothesis testing. Point estimates and interval estimates. In sampling, there are usually two types of estimates. 1. A point estimate is a single number that is used to estimate an unknown population parameter. 2. An interval estimate is a range constructed about the single point estimate by using the appropriate sampling distribution. The sample mean is the best estimator of the population mean, mu. Recall that the sample mean is computed by the sample mean equals summation x over n, where x is the value of an observation and n is the total number of observations. The sample variance, S2, and the sample standard deviation, S, are used to estimate the population variance and the population standard deviation. Recall that the sample variance and the sample standard deviation are computed. Sample variance equals summation, open bracket, x minus, x bar, close bracket, squared, divided by n, minus 1. Standard error of the mean. The standard error of the mean is the standard deviation of the sampling distribution of the sample means. The standard error of the mean is computed by standard error of mean equals standard deviation, over, square root of n. Chance difference versus a statistically significant difference. The question we need to answer is whether the difference between the mean of the population and the sample mean is real or whether the difference is due to sampling variation that we know can exist. This difference that could occur between the population mean and the sample means would be due to the sampling process. Such a difference is called a chance difference and is not considered a statistically significant difference. Type 1 and Type 2 errors. The decision has to be made based on a judgment concerning the seriousness of committing type I error. The general guideline is to set at a relatively low value, 0.01 or 0.05, if rejecting a correct null hypothesis would be very costly and or hazardous. Conversely, if accepting an incorrect null hypothesis, type 2 error is costly or hazardous, the value should be high, 0.25 or higher. A type 2 error has a prerequisite in that this particular error can occur only if the hypothesized mean is incorrect. Or it is often said that type 2 error can occur only if the true mean changes. Summary for Study Session 3. In this study session, please note the following. 1. Estimation involves estimating, or predicting, the value of an unknown population parameter, such as the population mean or the population proportion. In sampling, there are usually two types of estimates. A point estimate is a single number that is used to estimate an unknown population parameter. B. An interval estimate is a range constructed about the single point estimate by using the appropriate sampling distribution. 2. The interval within which a population parameter is expected to lie is usually referred to as the confidence interval. That is, an interval estimate is a range of values used to estimate a population parameter. For example, the confidence interval for the population mean is the interval that has a high probability of containing the population mean, mu. 3. A statistical hypothesis is a statement about the value of a population parameter that may or may not be true. 4. The difference that could occur between the population mean and the sample means would be due to the sampling process. Such a difference is called a chance difference and is not considered a statistically significant difference. Study Session 4. Confidence Intervals and Statistical Hypothesis Testing, 2 Samples. Introduction. In this study session, you will learn about sampling distribution of the difference between 2 sample means. The sampling distribution of the difference between 2 sample means. Analogous to what you did in Study Session 3, if you take all possible samples of n size, from a population of n, and compare the mean of each sample with the mean of all the other possible samples, you will find that the arithmetic mean of the difference in sample means is 0. Moreover, the differences will be normally distributed if the population is normally distributed or if the sample size is large. If the sample is small, the differences in the sample mean selected from a normally distributed population will be student t-distributed. The above should sound somewhat familiar to you since the sampling distribution of differences in 2 sample means is similar to the sampling distribution of sample means. Statistical hypothesis, about the difference between 2 population proportions. Just as we can test hypotheses about the difference between 2 population means, we can test hypotheses about the difference between 2 population proportions 1-2. In order to do this, we will select large samples so that we can assert that the differences between the sample proportions P1, P2 are normally distributed. The mean of the sampling distribution of differences between sample proportions P1, P2, is the difference between the population proportions 1-2. Summary for Study Session 4. In this study session, please note the following. 1. The samples of n size, from a population of n, and compare the mean of each sample with the mean of all the other possible samples, you will find that the arithmetic mean of the difference in sample means is 0. 2. That is, the sampling distribution of the difference in samples means will have a mean of 0 if the samples all came from the same population. Study Session 5. Statistical hypothesis testing for several population parameters, proportions, and means. Introduction. Chi-square, chi pronounced chi, tests provide the basis for judging whether more than 2 population proportions may be considered to be equal. Analysis of variance techniques provide ways to test whether more than 2 population means may be considered to be equal. This study session is intended to introduce you to statistical hypothesis testing and its procedure. Test for several populations proportions, analysis of nominal level data. The chi-square test. In statistical hypothesis testing, procedures were discussed for testing hypotheses with data obtained from a single simple random sample or from 2 such samples. You discuss tests by considering the goodness of fit and independence. 1. Tests of goodness of fit provide a means for deciding whether a particular theoretical probability distribution such as the binomial distribution is a close enough approximation to a sample frequency distribution for the population from which the sample was drawn to be described by the theoretical distribution. 2. Tests of independence constitute a method for deciding whether the hypothesis of independence between different variables is tenable. Conditions for applying chi-square tests. 1. Each observation or frequency must be independent of all other observations. 2. The sample size must be reasonably large in order that the difference between the observed and expected frequencies is normally distributed. 3. No expected frequencies or observations should be small. It is recommended that this expected frequency should not be less than 5, if it is less than 5, it should be merged with others. Characteristics of the chi-square distribution. 1. The computed value of chi-square is always positive because the difference between it is squared. 2. There is a family of chi-square distributions. There is a chi-square distribution for 1 degree of freedom, another for 2 degrees of freedom, another for 3 degrees of freedom, and so on. The number of degrees of freedom is determined by k, 1, where k is the number of categories. Therefore, the shape of the chi-square distribution does not depend on the size of the sample. 3. The chi-square distribution is positively skewed. However, as the number of degrees of freedom increases, the distribution begins to approximate the normal distribution. Tests of goodness of fit. The sequence of steps in performing goodness of fit tests is similar to previously discussed hypothesis testing procedures. 1. Null and alternative hypotheses are established, and a significance level is selected for rejection of the null hypothesis. 2. A random sample of observations is drawn from a relevant statistical population or process and a test statistic is selected. It is the chi-square distribution designated as. 3. A set of expected, or theoretical, frequencies are derived under the assumption that the null hypothesis is true. This is generally an assumption that a particular probability distribution is applicable to the statistical population under consideration. 4. The observed frequencies are compared with the expected, or theoretical, frequencies. 5. If the aggregate discrepancy between the observed and theoretical frequencies is too great to attribute to chance fluctuations at the selected significance level, the null hypothesis is rejected. Tests for equality of several population means. Analysis of variance test. The underlying assumptions in the analysis of variance procedure and their interpretation in the teaching methods problem are as follows. 1. Normality. 2. Independence. 3. Homoscedasticity. Analysis of variance procedure. It compares variability of means within populations with variability among population means. If the ratio of variance among the population is to some extent larger than variance within population, the H-nut is rejected. A major assumption is that the variances of the populations are equal. Test statistic equals F statistic. The computation may be approached as follows. The total variability in the data is split between and within. One-factor analysis of variance. When populations are distinguished on the basis of one criterion, we speak of a one-factor analysis of variance. Two-factor analysis of variance. When populations are distinguished on the basis of two criteria, we speak of a two-factor analysis of variance. For convenience purposes, we shall call the two factors row and column factors. Summary for study session 5. In this study session, please note the following. 1. Tests of goodness of fit provide a means for deciding whether a particular theoretical probability distribution such as the binomial distribution is a close enough approximation to a sample frequency distribution for the population from which the sample was drawn to be described by the theoretical distribution. 2. Tests of independence constitute a method for deciding whether the hypothesis of independence between different variables is tenable. This procedure provides a test for the equality of more than two population proportions. 3. The assumptions in the analysis of variance procedure and their interpretation in the teaching methods problem are normality, independence, and homoscedasticity. Study Session 6. Correlation and Regression Analysis, the Nonlinear and Multivariate Cases. Introduction. Relationships in the real world are frequently neither linear nor confined to two variables. In this study session, you will learn more about correlation and regression analysis, which also includes nonlinear and multivariate cases. Nonlinear two-variable cases. There may be times when the two variables which we are attempting to correlate should not be described by a linear regression equation simply because the relationship is not linear. In such cases, it would not be appropriate to use a straight line as the standard of perfect correlation. For instance, we might find that, while there is a definite relationship between x and y is changing geometrically by a given rate, while x is changing arithmetically by a given amount. Exponential regression and correlation analysis. Let us consider the first of the two nonlinear cases mentioned above, where y is changing by a certain rate while x is changing by a certain amount. The exponential regression equation. There are two ways in which this type of relationship can be expressed as a regression equation. It can be expressed in terms of yc itself, or it can be expressed in terms of the log yc. In the first case, the equation reads as follows. Y base c equals ab raised to the power of x. In terms of log yc, the equation is log y base c equals log a plus x log b. A close examination of the second equation reveals that it is a linear equation in its logarithmic form. In the log form of y, the relationship is linear. Looking at the equation written in this fashion, we can interpret the b coefficient. Specifically, b is 1 plus the rate of increase in the dependent variable as the independent variable increases 1 unit. Just as with other regression equations, it is possible to substitute a value for x and calculate yc. Coefficients of correlations and determination. The quality of the relationship between the two variables can also be measured using the exponential equation as the standard of perfect correlation. Second-degree arithmetic regression and correlation analysis. There may be times when neither a linear regression equation nor an exponential equation fits the data displayed in a scatter diagram. In such a case, one might consider a second-degree or second-order arithmetic regression equation. The general form of the regression equation for a second-degree case is y base c equals a plus bx plus cx squared. Unlike the linear equation and the log form of the exponential equation, the slope of the second-degree curve is not constant. Rather, the slope varies as x varies. However, is still the intercept, the value of yc when x equals 0. If we use the least squares method to solve for the values of a, b, and c in the equation, we utilize the following normal equations. 1. Summation y equals na plus b summation x plus c summation x squared. 2. Summations I equals a summation x plus b summation x squared. 3. Summation x squared y equals a summation x squared plus b summation x cubed plus c summation x, raised to the power of 4. Second-degree correlations analysis. The quality of the relationship between the two variables, as expressed by a second-degree regression equation, can be measured using the following equation for the coefficient of correlation. R equals a summation plus b summations I plus c summation x squared y, minus, ny bar squared, divided by summation y squared, minus ny bar squared, all square rooted. Multivariate regression and correlations analysis. Multivariate linear correlation and regression analysis is just an extension of the simple linear case, so that there is more than one independent variable. Thus, the assumption regarding only two variables, one dependent and one independent, is relaxed. Each independent variable, however, is linearly related to the single dependent variable. The basis for multivariate correlation and regression analysis may be explained in terms of the variation of the dependent variable. The larger the proportion of the total variation that can be associated or explained with the independent variable, the higher the coefficient of correlation. Assumptions about multiple regression and correlation. The assumptions are: 1. The independent variables and the dependent variable have a linear, or straight line, relationship. 2. The dependent variable must be continuous and at least interval scale. 3. The variation in the difference between the actual and the predicted values must be the same for all fitted values of y, that is, yc must be approximately the same for all values of yc. When this is the case, differences exhibit homoscedasticity. Further, the residuals, computed by yc, should be normally distributed with a mean of 0. 4. Successive observations of the dependent variable must be uncorrelated. Violation of this assumption is called autocorrelation. Autocorrelation often happens when data are collected over periods of time. 5. The independent variables should not be highly correlated with themselves. When the independent variables are highly correlated, it is called multicollinearity. Multivariate regression equation. Recall that the simple linear regression equation encompassing one independent and one dependent variable has the form yc equals a plus bx. The multivariate regression equation takes the following form. Y base c equals a plus b1 by 1 plus b2 by 2 plus. Consider a regression equation with three variables, a dependent variable, and two independent ones. The equation would be y base c equals a plus b1 by 1 plus b2 by 2. Multiple correlation. Like simple linear correlation, we can compute a measure of the quality of the relationship between the dependent variable and the independent variables. The measure is called the coefficient of multiple correlations R, and 2 South African rand is the coefficient of multiple determinations. R2 can be interpreted to mean the proportion of the total variation in the dependent variable, which is explained by changes in all the independent variables. Multiple correlation equals regression sum of squares, divided by the total sum of squares. Coefficient of multiple non-determinations. Logically, the coefficient of multiple non-determination measures the proportion of the total variation in the dependent variable y that is not accounted for by the independent variables. It is found by 1, R2. Adjusted sums of squares method of determining multiple regression equations. Solving the normal equations required to carry out multiple regression analysis can be rather laborious. Using the adjusted sums of squares method reduces the number of normal equations by 1 and, therefore, simplifies the task somewhat. Summary for Study Session 6. In this study session, please note the following. 1. The two variables which we are attempting to correlate should not be described by a linear regression equation simply because the relationship is not linear. In such cases, it would not be appropriate to use a straight line as the standard of perfect correlation. 2. The statistical techniques discussed in this chapter appear to work well even when one or more of the following assumptions are violated. Even if the values in the multiple regression equation are off slightly, our estimates based on the equation will be closer than any that could otherwise be made.